Today I am going to begin chapter number 2 called as computer hardware. I am going to begin with the logic circuits. Before I could go, let me give the history part of the Boolean algebra for a minute or two. Right? For centuries, mathematicians felt that there is a link between logic and the mathematics. Nobody could ever find this link between these two except George Woolley way back in 1863. He was the one first to realize that he could connect the logical thinking and the mathematics. He wrote certain journals and published. Afterwards he died. After 83 years, Dr. Claude Shannon took up the concepts of George Woolley and introduced the circuit theory in telephonic circuits. Then engineers felt that why can't we use these circuit theories even into the computers. Here I am going to begin the concept known as logic gate. What is logic gate? Gates are digital circuits because they have certain inputs and the output signals either in the form of a high or low. High means is also known as 1. In other words, we also call it as on. Low means is represented by a digit 0 or is also quite often we call off. Now today I am going to introduce logical gates. There are primary gates and the secondary gates. What are the primary gates? They are, the first gate is NOT gate, second gate is AND gate, and third gate is OR gate. Now, with the help of these three gates, we can also generate another 4 more gates. They are known as secondary gates. These 3 gates are called as primary gates. With the help of that, NOT and AND is called as NAND gate. NOT and OR is called as NOR gate. NOT and AND is called as NAND gate. NOT and OR is called as NOR gate. We also have the 6th gate is known as XOR gate. In other words, exclusively OR gate. Then the 7th gate is known as XNOR gate, which is inverted, opposite of NOR gate. Now I am going to quickly explain 7 gates. Let me begin. The logic circuit or circuit diagram goes like this. This is called as an AND gate. This is the circuit diagram of AND gate. Here is an A is the input and B is an input. When it comes out, it becomes A dot B. Dot is represented as AND. Then OR gate is represented like this. This is the logic network, circuit diagram of OR gate. Here is A is the input and B is the input. When it gets into the circuit, it is known as A plus B. Please note, boys and girls, plus does not indicate any addition. It's an operator which represents a gate called as OR gate. OR is represented as dot. These two are called as binary gates. These two are called as, because it has by two inputs are there, A and B. This NOT gate is known as an unary gate, which has only one input. In other words, it's a inverted gate or a negation. When you give 0 volts, other end it gives you 230 volts. If you give 230 volts, it gives you 0 volts. That's why it's called as inverter or negation. Here, this gate is known as an unary gate, which will have only one input. For example, if you have an input called as X, when it goes through this circuit diagram, it becomes X complement. Why it is called as unary gate? Because it has only one input. So these three gates are known as primary gates. Primary gates. With the help of these three gates, the rest of the four gates can be built. One is called as NAND gate, which is NOT and is called as NAND gate, and NOT and OR is called as NOR gate. Here I go. How do we represent NAND gate? Let's say P is the first input and Q is the second input. When it goes to, this is an AND gate, here you have to give a circle. So this becomes a NAND gate. This becomes a NAND gate. So NAND gate, NOT and is called as NAND gate. Similarly, here we go NOR gate. NOR gate is represented like this. P is the input, another one input is Q, it becomes P or Q. When I do this NOT and OR is called as NOR gate. So this is called as NAND gate. This is called as NOR gate. Let me go in for the XOR gate, which is the sixth one, which is called as an exclusive OR gate. What does this mean? Here is the first input P, this is the second input Q. When you have double curvature, then it's known as a XOR gate. XOR is known as an exclusive OR gate. Here we represent XOR gate like this. P XOR Q. XOR is denoted as plus S rounded off. Plus S rounded off. And the last seventh gate. Here are the three gates which are primary gates, and these are called the secondary gates, including this. Fourth one is called as XNOR gate. Inverted XOR gate. Inverted XOR gate. It's known as XNOR gate. Here, XNOR gate is denoted as a dot is rounded off. This we known as XNOR gate. Now I am going to elaborate. I am going to construct the circuit diagram for the given Boolean expression. Number one. Number two, what are the applications of Boolean algebra? How are you going to implement? Here we say these 7 gates are very, very crucial. One need to be familiar with all the 7 gates. I repeat again, these 3 gates I segregate like this. Primary gates, they are called as secondary gates. Primary gates are the secondary gates. These gates are built based on these 3 gates. NOT and is known as NAND gate. NOT and OR is called as NOR gate. Exclusive OR gate and XOR gate is denoted like this. In this case, NAND gate is Now that I am going to begin construction of a circuit diagram based on the given Boolean expression. Now I repeat again. Let me recapitulate what has been done so far. These primary gates, you will be given a question even in ISA. They will give a Boolean expression. Based on the Boolean expression, you need to construct the circuit diagram. Here I will give an example. Here are the few examples of it. We shall do it right now. Boolean algebra is almost useless unless and until it is translated into circuit diagrams. Here are the few examples. I will take away straight away. We shall construct the Now we are going to construct the circuit diagram for the given expression f. F is the given Boolean expression. We need to construct the circuit diagram for this. Let's see that. From our basic, we need to move from left to right. We need to move from left to right. First of all, here we have a gate called as AND gate is available, so this needs to be drawn like this. And here is another one gate, it again AND gate, which is A and C. C can be written as like this. And here the three variables are there. That is B, A, and C. Boys and girls, though it is called as a binary gate, we are expected to have only two inputs. Here also two variables, here also two variables. Here three variables are there. Are we allowed to put three inputs in a one binary gate? Practically speaking, technically speaking, which is not allowed. But council does exempt. You are allowed to give two or more inputs in a binary gate with or without complement, without mentioning this NOT gate. Here I go. What would be the outcome of this gate is, it becomes A and B. Here is the intermediate answer. This is A and B. What would be the intermediate answer would be? This is the input A. It goes into this NOT gate. C becomes C complement. So the intermediate answer would be A dot C complement. Similarly here, B complement and A complement and C. So all the three of them have been joined by an OR gate. So this would be to a final output called as F. What is the intermediate answer is? A dot B. Here A dot C complement. Here B complement, A complement, C. So this is how we construct. If required, we shall do one more. Now that I am going to explain the XOR gate and XNOR gate with the help of a truth table. truth table. Circuit diagram we have seen a little while ago. Here I go. What is these two are called as XOR gates. XOR is denoted as plus is rounded off. A XOR B. P XOR Q XOR R. First of all, if we finish XOR gate, then we shall go to XNOR gate. As the symbol signifies, it's a XOR gate. What is the XOR gate output is? The output of a XOR gate is 1 when there are odd number of ones as inputs. Here, how many inputs are, how many ones are here? Only one, it's an odd number. How many ones are here? 1, which is an odd number. How many ones are here? 2 ones are there, which is an even number. If there are odd number of ones in input, the output is 1. If there are even number of ones, then the output is 0. How many ones are here? 0. 0 is an even number. So this is how the XOR gate works for two variable truth table. Here I am going to give XOR gate with three variables, namely P, Q and R. If you look at here, how many ones are here? 0 ones are there. Hence it's an even number. The output is 0. How many ones are there? 1 is there. It's an odd number. Hence the output is 1. How many ones are here? 1 is there. The output is 1. How many ones are here? 2 ones are there. It is an even number. The output is 0. Here how many ones are there? 1. The output is 1. How many ones are here? 2 ones are there. It is an even number. How many ones are there? 2, which is an even number. The output is 0. How many ones are there? 3 ones are there. So the output is 1 because 3 is an odd number. Here is an example of a XOR gate with two variables. Here is a second example, XOR gate with 3 variables. The main point to be understood here is, if there are odd number of ones, the output is 1, otherwise the output is 0. In this case, we have seen two variable truth table of XOR gate, 3 variable truth table of XOR gate. Now we shall move to the XNOR gate. XNOR gate means just the NOT and XOR. In other words, inverted XOR gate is known as XNOR gate. Here the output is 1 if there are even number of ones are there. Here how many ones are here? Here how many ones are there? 2 ones are there, which is an even number. The output is 1. Here how many ones are there? 1, which is an odd number. The output is 0. How many ones are here? 1, which is an odd number. Here how many ones are there? 0. 0 is an even number. So here is an example of a XNOR gate where the output is 1 if there are even number of ones as inputs. This is an example for 2 variable XNOR gate. Here is an example of 3 variable XNOR gate. Here I have a look, boys and girls. Here how many ones are there? 0 ones are there, which is an even number. Here odd number. Here odd number. Here even number. Here odd number. Here even number. Here even number. Here odd number. So this is an example of 3 variable XNOR gate. Here is a 2 variable XNOR gate. Now we have learned the truth table for XOR gate and XNOR gate. Now I would like to tell you about the universal gate. What is this universal gate is all about? The NAND gate and NOR gate are called as universal gate. This can be built based on the AND gate and OR gate is very easy to design and it's an inexpensive affair. It's a cost effective. That's why we call NAND gate and NOR gate as a universal gates. Now, based on the NAND gate to NAND gate, NOR gate to NOR gate, we are going to construct, we are going to draw certain circuit diagrams. We shall see how to go about it. I repeat again, what is a universal gate? NAND gate and NOR gate are universal gate. Why it is called as universal gate? It's based on AND gate and OR gate, which are very easy to design, and it's a cost effective way of manufacturing. It's very, in other words, low cost, inexpensive affair. That's why we call it as a universal gate. Now I am going to teach you the next concept is called as NAND to NAND gate and NOR to NOR gate. Before we go to NAND to NAND gates or NOR to NOR gates, I would like to tell you two different terms which we call it as SOP and POS. What is this SOP? Is sum of products, and POS stands for product of sum. As you have learned in the first chapter in Boolean algebra, SOP is denoted by a symbol called as sigma. Sigma is sum of products. What is POS is? We have an operator which is pi-like. Which is? So we will be using SOP and POS. SOP will be used for NAND to NAND gate and POS will be used for NOR to NOR gate. Here we are going to do a couple of examples. How do we construct NAND to NAND gate and NOR to NOR gate? Here I go. I am going to draw the circuit diagram for this very simple expression called as now I am going to do the normal circuit diagram for x, y, z complement plus z x complement. And I am going to use even the NAND to NAND gate form. The simple expression goes like this. This is the input x, this is the input y, and this is input z. All are connected by an operator. Similarly, this is z and this is both are connected by a XOR gate. This is what you are given function f. So what is the intermediate answer for this is x and y and z complement. X, y, z complement. Here z, x complement. When you add together, what would be a f would be x, y, z complement plus zx complement. This is the normal way of doing it. Same expression I am going to use NAND to NAND gate. I am going to use NAND to NAND gate. I have counsel two advice. Instead of drawing this NAND gate, you are permitted to write, because in one of the questions gate itself, you are allowed to use variables and their complements as inputs. They give one clause where straight away this NOT gate need not be drawn. Instead, what we can do is straight away we can do like this. This is also allowed. Even if you do so, NOT gate need not be mentioned. Even if you do so, you will be given the full mark, because to draw this gate would have this time consuming. They hardly allocate very few marks. So to draw this diagram, you will be given just a mark. You need not draw this, because one of the clauses you are allowed to use variable and their complements as inputs. Two or normally AND gate is a binary gate. Binary means true, but there are three inputs are there which is exempted, because the counsel in your question paper, ISA question paper itself, they do tell you assume that two or more than two inputs can be used in AND gate or OR gate technically, which is untrue. Here also NOT is not mentioned, like this need not be written. Straight away you may write Z complement. Draw the line, you may write Z complement, that is also allowed. Now I am going to use NAND to NAND gate for the very same expression. Same expression, I am going to do it NAND to NAND gate. What do I do is, this is the X, this is your Y input, and this is your Z complement. All of them are connected by an AND gate. Not an AND is called this NAND gate. Similarly, what the second expression is? This is Z and this is X complement is also connected by not AND gate to NAND mix. Here is a NAND gate and this is also connected by a NAND gate. So here is an AND gate and here is an AND gate. Here is an AND gate and here is an AND gate. What happens is you get your original function f out here. So this is what NAND to NAND gate. NAND to NAND gate means the first and foremost step is you have to derive the SOP, that is sum of product. Whenever you are using NAND to NAND gate, whenever we are using NAND to NAND gate, what needs to be done is you have to derive the SOP, then draw the logic diagram, and with the help of a AND gate and OR gate. This is the example of a NAND to NAND gate. Let me quote one more example of a NAND to NAND gate. Here I will change the expression instead of this. Second example we shall do it. Same NAND to NAND gate. Here is a function f. Here is a function f where AB plus BC plus CA. Here, what do I do is, I am going to construct a logic network with the help of a NAND to NAND gate. What is the given expression is? AB plus BC plus CD. Here I go. Here is an A, this is a B. So this becomes AB. The next one is what is the point out here is, here I use a NAND gate, not an AND, not an AND, not an AND. If you use twice, nan to nan. If you use twice, you get back the original given expression. You get back the original given expression. We shall also see the next concept called as not to not be. Here is an example of a not to not be. We shall see. To do the not gate, three simple steps are there. The very first step is to get the POS. POS means product of sum. Then draw the logic circuit diagram with the help of an OR gate and gate and apply the NOT twice. Here I take an example of a NOT to NOT gate. Should I give an example? Look at here is a first term, second term, third term. This is called as POS, product of sum. Now you have been given this expression F. Now we need to construct a logic network with the help of a NOT to NOT gate. To do so, the very first step itself is to derive the SOP. This itself is a POS. Now what we do is we draw the circuit diagram for a gate called as OR gate. This is X is the input and Y is the input. NOT and OR is called as XOR. What the second expression is? Y and Z. It again, NOT and OR becomes what? XOR. NOT and OR becomes NOT. And third expression is Z and X. All of them needs to be connected. Yet again with a NOR gate. Yet again with a NOR gate. This becomes your function F. The NOR gate has appeared twice. So if you have a NAND gate and NAND gate, you get back the original expression. As we are using the NOR gate and NOR gate, you get back. So what happens is the first step is to derive the simplified POS. This is the no redundancy, no repetition. So this is simplified POS, means product of sum. The second one is draw the circuit diagram, and third one is apply the NOR gate in two places, which will get back to your working expression. So we have seen what is the universal gate, we have seen the NAND to NAND gate, we have seen the NOR to NOR gate. Now we shall go to the applications of gates. How these gates are useful in our day-to-day life? As all of you know, in your CPU there are very many units are there. One of them is called as ALU, arithmetic logic unit. How does it work? So your work is divided into multivarious parts. For example, you have adders, you have encoders, you have decoders. I'll tell you what is the role of a adders, what is the role of a encoder, what is the role of a decoder. What is exactly the adders? Adders means there are two different types of adders are there. One is called as half adder, another one is called as full adder. Half half adder will have a 2-bit information and full adder will have a 3-bit information. First of all, let me tell you what is an adder is. We are conversant with only the decimal number system. In short, ternary number system. We use in our day-to-day life all the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, it's 0 to 9. 10 digits we use it. That's why it's called as ternary digits or decimal digits. Whereas computer won't understand. Computer will be able to understand in terms of zeros and ones. In terms of zeros and ones. How do we do it? Who does this? Whatever if I wanted to feed a number called as 9 from my keyboard, computer would understand what is the digit 9 is all about. So the 9 is taken, you have one of the circuit is known as an adder, the 9 is taken, the 9 is converted as 1001. Converting from decimal to binary is known